This is a quick overview of the new content in Gravity Engine 6.0. The content is also, as usual, summarized on the 6.0 documentation, on the web page, and in the README file contained within the asset. So there's some new stuff right away just in the Gravity Engine Inspector. We can see here there's a new checkbox called XZ Orbital Plane, and this is checked by all of the elements that generate orbits, so orbit universal, dust ring, binary orbit. And what it does is it places the orbit, instead of in the normal physics literature in the XY plane, it places it in the XZ plane. This feature was requested by a number of users because the default navigation in the Unity editor is to makes it easier to move across the XZ plane, with Y being the up direction, and they wanted the orbits to match that natural sense. It does mean that if you're transcribing information from the physics literature, particularly R vectors and velocity vectors, you need to be aware of the fact that that flip has occurred. In addition, there is a center of mass control in the Gravity Engine Inspector. So if you wish to fix the center of mass so that as bodies are added, the net center of mass velocity stays constant, you can tick this box. And if you wish to locate the center of mass at a particular position, you can do that, and the net result is the objects in the scene will shift around as appropriate to result in that center of mass. This feature came up because in some cases, if you have a planet with a number of heavy moons and you're using orbit universal, the moons are given velocities, but the planet isn't given a compensating velocity around the center of mass, because we just treat it as a simple, essentially one body system, not as a binary object in that case. And you can get a bit of center of mass drift. So one alternative is to put a fixed object marker on the central planet. The other is to use this Gravity Engine feature. If we open up the Advanced tab, we see there's also some new content here to do with optimization. In looking at where the time was spent when you go to large N scenes, so lots of N bodies, lots of massive N bodies, it turns out that the orbit predictors are a very high consumer of CPU resource, and that's because every frame they're taking the R and the V and regenerating the orbital elements. So there are two things that were done to optimize that. One is you can change the have that happen every frame. You could change that to be spread out over 5 frames or 10 frames, and that has a positive impact on the performance loading. The other thing you can do is you could, if you have Kepler scenes and the center body is not moving, there's now code that will check that, and in that case there's no need to recompute the orbit, and it's not recomputed unless there's been some change in it through apply impulse or because the center has moved in some fashion. So those optimization routines are documented with a whole bunch of performance numbers on the system. And in fact, the frame rate tester has been upgraded substantially and now writes data to a CSV file. So if you want to do your own performance profiling, you can. The other thing to note is that performance profiling in the editor versus in an actual application can be quite different. So let's go on to another feature in Gravity Engine, which is in fact the scene we have here, which is the binary orbit scene. So this scene is now in the tutorial section, binary orbits. So binary orbit now replaces binary pair, and the binary orbit class itself inherits now from orbit universal, as opposed to the old binary pair, which only inherited from ellipse. So that means you now have all the same parameter choices that you have in orbit universal. You have the option to do Kepler or not Kepler. This object also implicitly creates an N-body object of mass 0, and it says here generated by binary orbit, and that's to represent the center of mass, and that means that we can now attach orbit predictors to the planets, and those orbit predictors can have as their centers, so if we go in here and have a look, they can have as their centers the binary object, and that means that when we press play we can see the binary orbits with respect to the center of mass. this binary object can also itself have an orbit universal, so it allows you to place the binary pair in orbit around some other object, which is what we've done here. We've placed it in orbit around a star. In this case, we've used Kepler's mode for everything because at this distance, the star would gravitationally disrupt this binary very quickly in less than an orbit. So by putting it in Kepler mode, we put it on rails, and we don't get the correct n-body physics, but we get what we might want to have in our game scene. If we go ahead and press play, we can just see how that looks. And away goes the binary in orbit around the star. There's a new mini game in 6.0. So if we go into the minigames folder, there's this folder on Rails Moon to Earth. And this allows us to kind of complete the job that was started with the maneuver planning of the free return scene. So we just quickly press play here to see what this scene is about and hit space to pause things. What we have is we have a spaceship in orbit around the moon, and what we're planning is the injection burn, the trans-Earth injection burn. So in this case, it's telling us that our Earth periapsis is going to be 13.67. And if we look at in the inspector, the on-rail moon to Earth, the variable that we control is the escape velocity fraction. So you'd want this to be greater than 1 because you're trying to escape the moon. And depending on how that's changed, you will change the periapsis that you reach going around the Earth. This scene is described in a new video tutorial and is an on-rails scene, and that's because the three-body dynamics are very complicated and quite twitchy and sensitive to initial conditions, so by using a patched conic on-rails approach, we get a much better behaved mission planning scene. I'll just give that a pause. And then the next thing I want to talk about is a fairly simple little new demo scene, which shows off the rocket engine class. So there's a new rocket engine called Ion Rocket Engine, and there's a scene that goes with that called Ion Engine. And what this does is it does a constant thrust in the direction, basically prograde, and I beg your pardon, retrograde. You're thrusting behind, you're moving forward. And so what you see here is that the trajectory prediction shows that the orbit will spiral outward because of the continuous thrust, and then when the engine shuts off, it'll stay in a circular orbit at the end. And so that's an example scene of how to write a continuous thrust rocket engine. In addition to that, as new content, there's a few utilities that help provide with debug. So for illustration purposes, I have added them to the getting started transfer with orbit point scene. So let's go ahead and find that. So we want to go into the getting started, transfer ship with orbit point. So what I've done I've created a new object, GE debug, and I've added a couple of things that are just handy utility functions. So GE maneuver display, orbit compare, and distance. And so in this scene, we can go ahead and start. And so it's showing you the difference between the spaceship and station orbits, the distance between the spaceship and station. And if we hit X and set up some maneuvers, we see in this maneuver display script the maneuvers that are pending. And we also see the current time. And I have begun the process of annotating the maneuvers with a label, and in this case it's generated by the Hohmann general circular Hohmann velocity subtype of the Hohmann general code. And hopefully those are useful to you. That summarizes the content in Gravity Engine 6.0. I hope you find it useful. If you have questions or find anything that doesn't look right to you, please let me know at nbodyphysics@gmail.com. Thanks.